So we're going to continue with optimization, right? Finding maximum and minimum values of various functions. But here we're going to use a technique called Lagrange Multipliers. So it's somewhat of a more elegant way of doing optimization, and maybe a little more sophisticated as well. It has, uses in mechanics and dynamics. Anytime you have sort of constrained forces, so if you have an inclined plane and you have a weight or a block on the plane, then the block is constrained to move right in the plane. So that's one way to think of a constraint. And there's other examples too, but that's just one. So we're not going to do those types of examples here. We're going to do just more of the same variety that we did in the last couple of sections. So I'm going to start with the first example. Find the maximum value of the function f of xy. There should be a y here as well. It depends on both x and y. And the function is x plus 2y. There we go, f of xy. So we want to find the maximum value of that function on the circle x squared plus y squared equals 4. So that's just a circle of radius 2, right? And, this is something you should know how to do already. Well, even in Calc 1 you knew how to do this. And maybe we'll do it that way later. But let's think of this using Lagrange multipliers. So first of all, before we even get to the Lagrange multipliers, let's take a look at what we're trying to do here, right? So one way to think of it is, right, f of xy, z, as a function of x and y is just x plus 2y. And you should recognize that this is just a plane in space, right? It's the usual equation of a plane, right? And in fact, it passes through the origin because it equals 0, right? So here's the xy plane, right? And let's say that, well, then I should use a different color here. So here's the xy plane, right? And then here's the plane, right? Z is equal to f of xy, right? X plus 2y. And in the plane below here, there is a circle, right? This is just the circle of radius 2 equals 4, right? And so you can see what we mean by the maximum value, right? The maximum value is just the highest point on the plane that's above the circle, right? So right about here, so this would be on the circle, that would be the highest point. That's the maximum value, the maximum z value, of course. So there's a z-axis here as well. Right. And you can also see where the minimum value is. So there is also a minimum value over here somewhere. That's the lowest point on the plane that's above the circle. Okay, so yeah, this picture should make it clear that obviously if we're just talking about the plane itself, the plane keeps going up forever. There is no maximum value and there's no minimum value, right? You can make z as big as you want, just make x and y as big as you want. Or you can make z as negative as you want, just make x and y as big of negative numbers as you want, right? But if you're constrained to move right on the circle, then that limits what x and y can be. And so that limits what z could be, right? So there's the picture, and hopefully that helps. But now we're going to think of it a slightly different way here. Okay, so here's the circle on the right here. So this is just x squared plus y squared equals 4. Right? So the radius is 2. So these numbers are very tiny here. You can't see them, but this is 1, this is negative 1. Right? This is y equals 1, y equals negative 1. And so this point up here would be 0, 2. Right? This would be 2, 0. Oops. I guess I got to go inside the circle here. And so on, right? So this is just the circle of radius 2, right? So we can think of this right, as a function now. So I'm going to call it g of x and y. It's just x squared plus y squared. Oh, and if you want it to equal 0, then just subtract 4 from both sides, right? So this is called the constraint equation. I think we mentioned that earlier. Right, so this forms the constraint, right? This is, we're only looking at points on the circle, right? Not inside the circle, by the way, only on the circle. So this point here, right, is not on the circle. This point here, right? So these are all interior points to the circle. We would say they're on the disk of radius 2, but not on the circle, right? So the disk would include all the points inside the circle as well, but we're not going to consider those. We're only considering the circle itself, right? And the function we want to, in this case, maximize, although it could be minimize as well. So x plus 2y, right? This is the objective, right? We can call this the objective function. Right? This is what we want to optimize, and in this question we want to maximize it. Right? Okay. So now that we're in 2 dimensions here, right? This is the x-axis and the y-axis here. Here's the x-axis, right? Here's the y-axis. So the z-axis is coming out of the screen directly at you. So I'm not going to be able to draw it here, right? So here's the z-axis coming out of the board. Think of an arrow just coming straight out at you. Yeah, right-hand rule, right? So if you point your fingers in the x direction on your right hand and then curl them in the y direction, your thumb points directly at you. You're pointing at yourself with your thumb. All right. So the objective, right, so instead of thinking this as a plane, right, we're going to think about the level curves of this function here, right, x plus 2y. Right, so in other words, we just want x plus 2y to equal some constant, c. I can't move up too much here. So again, let's just make up some numbers for c here, right? Suppose we want x plus 2y. Let's start with c equals 0. Right, so we know what this is. This is just a line, y equals negative 1/2 x. And that line will look something like this. Okay. Right, so that's one line, and if, let's say, c is equal to 2, I think we would get this line here. Right, so just a different y-intercept, right? If c is negative 2, you get this line, and so on. And these are rather sloppy, so instead of doing that, why don't I just graph a whole bunch of these using the software I'm using here. Okay, so that's a little bit better. And in fact, I labeled the C's for each of these, right? Yeah, to make it clear, right, C is, or I think it's 2C is the slope, is the y-intercept, right? C over 2 is the y-intercept. So in other words, if I solve this for y here, I get y is equal to negative 1/2 x plus c over 2. So c over 2 is the y-intercept. Okay, so I'm just graphing a whole bunch of these lines for different values of c, and you can see the c's are here on the right in red. I hope you can read that. It's a little, should make it darker, but hopefully that's clear. So what I want to do now is let's start with the objective function up here. That's the f, right? And let's just take the gradient of that. So the gradient of f, right, remember, is the vector where the first component is just the x partial of f. The second component is the y partial of f, right? There is no z, right? There's no z variable here, right? So it's just a vector in the plane, 2 dimensions, right? And in this case, the x partial is just 1, and the y partial is just 2, right? So this is just a constant vector, right? If you like, I plus 2j, right? And as we expect with this, if I draw the vector, it's going to be perpendicular to, or normal to the level curve. In this case, it's not a curve, it's a line. But yeah, the gradient vector points normal to these level curves here, right? And I realize I'm not drawing them correctly, because if I were drawing them to scale, right, what would that be? 1 would be about this much, and 2 would be there. So these vectors should be a lot longer than this, right? So these are the normal vectors to each of these lines, right? They don't change based on the line, based on the level curve, based on C, right? All these vectors are the same regardless of C here, right? So yeah, they're all just constant vectors. But they do point in that direction. So maybe, yeah, so I'll draw one way down here because I don't want it to interfere with the other vectors, right? But the point is that all these vectors are just perpendicular to the level curve, right? So we saw that a few sections ago, that the gradient points normal, meaning perpendicular, to the level curve. Okay. All right, now let's do the same thing for the constraint function, g of xy. So let's take the gradient of that. Right, so that's just gx, gy. In this case, the x component is 2x and the y component is 2y. Right, so this is not a constant vector here. This depends on x and y. So I can make an x a little bit bigger. 2xi plus 2yj, right? So, right, so this is for the circle here, right? So for the circle, these vectors point outward to the circle. They point this way. Again, maybe I don't have the magnitude correct, or even the direction. Let me make that clear here. Oh, I can do a better job than that, right? Especially here, that's just pointing outward, pointing outward, pointing outward, and so on, right? So all these vectors to the circle point outward, radially, right? They point radially outward from the circle. Okay? So, right, so notice that what I'm missing here is one line in particular that is tangent to the circle, but that's a level curve. So I'm going to do that in green, kind of a dark green here. So right around here, there's this level curve, which looks like 4.5, right? Looks like C is about 4.5, somewhere between 4 and 5 anyways, right? Right. And what I want you to notice about this particular point right here is if I draw the gradient of f, it points this way, right? And if I draw the gradient of g, well, it's outward from the circle. It also points this way too, right? So, in fact, that's the only place, I think, where the gradient of g, so that's the one in blue here, right, is in the same direction as the gradient of f, right? It may not be the same magnitude, right? One might be longer than the other. I'm not sure which, but it doesn't matter, right? They point in the same direction. Right? And if you're observant, you'll notice that there's another place where it does that on the circle. Way down here, if I draw this level curve for f, right, and the gradient of f still points in this direction, but now the gradient of g points outward from the circle, so it points this way, right? Is that clear? Yeah. So they don't point in the same direction, they point in opposite directions, but notice that the gradient of f, which is this vector here, is still parallel to the gradient of g, right? So whether they point in the same direction or the opposite direction, they're parallel vectors. Right? And remember what parallel vectors means. If the gradient of f and the gradient of g, are parallel, then there is some constant multiple of one to get the other, right? Now, I'm using c for that constant. The problem is I'm already using c for something else, the c for the level curves, right? And of course, they may not be the same c. They probably aren't. So I'm going to use a different letter for the constant multiple. I'm going to use the Greek letter lambda. Right? So this is the Greek letter lambda, right? And it's just a number, right? It's just a real number. Right? It's essentially what you have to multiply the gradient of g by to get the gradient of f. Okay? So at this point down here, right, lambda should be negative, right? Because you need a negative number. It points in the opposite direction. Oops. If you're talking about this point up here, right, now lambda should be positive, right? And don't read anything into the arrows here, right? It looks like lambda might be, I don't know, 1.2 or something, 1.1, 1.2. But it's a lousy picture, right? The picture is just there to show you that the two vectors are parallel, right? So this is the condition for two vectors to be parallel. Parallel, if I can spell, to the gradient of g, right? Okay. So yes, this lambda, which is a number, this is going to be called the Lagrange multiplier. Right? And let's see how it works, right? So we already took the gradient of f. It's up here, upper right. So that vector is the vector 1, 2, right? And here's the lambda. And then the gradient of g, that's this thing right here. That's just 2xi plus 2yj. Hang on, I didn't want to do that. So here it is again. Lambda times the gradient of g, which is 2x for the x component and 2y for the y component, right? Now remember, this is a vector equation, right? Lambda is a scalar, So that means I can multiply each component by lambda, and that looks like an x, right? So this should be a lambda. Let's try that one more time. There we go. And then 2 times y times lambda. Right. But because it's a vector equation, right, there's actually 2 equations here. Right? What are the 2 equations? One equating the x components and one equating the y components. So for the x components, we get 1 is equal to 2x lambda, and 2 is equal to 2y lambda. So we get 2 equations in 2 variables. Actually, we don't know what lambda is, right? So this is 2 equations in 3 variables, right? The 3 variables here are x, y, and lambda. So 2 equations is not enough, right? We're not going to be able to solve this system of equations because we don't have enough equations. We have too many variables, not enough equations. Okay. However, there's one equation that I'm forgetting about, and that is the constraint equation, this right here. So that has to be part of the system of equations as well, right? So this is x squared plus y squared minus 4 equals 0. Or you can also just write it as x squared plus y squared equals 4. Same thing, right? So now we have 3 equations in 3 variables. Okay, so let's solve this system here, right? We want to solve this system of equations, right? And these are nonlinear equations because we have x times lambda, y times lambda, and obviously x squared and y squared. So this is a nonlinear system, which are generally more difficult to solve. Right? So what can we do here? So there's 2 ways of doing this. Well, there's probably more than 2 ways. There's a few ways of solving the system of equations. One way is to solve the first equation for, let's use x here, right? So I have to divide by 2 lambda. So x is just 1 divided by 2 lambda, right? And do the same thing for y, right? If we divide by 2 times lambda, we just get 1 over lambda, right? 2 divided by 2 is 1. Okay, so now I have expressions for x and y in terms of the multiplier lambda. Well, if you look at the third equation, I can plug each of these in here to get an equation in lambda. Right? So now equation 3 reads 1 over 2 lambda, because that's x, right, squared, plus 1 over lambda, that's y, right, squared, and that still equals 4. So we can solve this for lambda. And if we do that, what do we get? We get 1 over 4 times lambda squared, right? 1 over 4 lambda squared, plus 1 over lambda squared, that's still equal to 4. Right? And if you get a common denominator here, you notice that I can multiply top and bottom by 4. And what that gives me then is 5 over 4 lambda squared equals 4 over 1. Right? Cross multiply. And I think we get 16 times lambda squared is equal to 1 times 5. So lambda squared, that's supposed to be a 6, is just 5 over 16. So take the square root, right? It's plus or minus the square root of 5 over 4. Okay, great. So we accomplished our goal here. We solved for lambda, but that really wasn't the answer to the question, right? The question was to find the maximum value of f being x plus 2y. Right? So we really didn't care what lambda is. What we care about is x and y. Right? But if you look up here on the upper right now, I have x equals 1 over 2 lambda. So what's 1 over 2 lambda? it's 1 over 2 times, well, plus or minus, so let's take the plus lambda first, right, the positive lambda. So this will be the square root of 5 over 4. And I think I have just enough space here. This is going to be 2 over the square root of 5. So, yep, so for lambda is equal to square root of 5 over 4, we get x is 2 over the square root of 5. Right? And I'm not gonna rationalize the denominator. You can if you want to. Right? And that's a 5, not an s. There we go. And what's y going to be? 1 over lambda is 1 over the square root of 5 over 4. So this is 4 over the square root of 5. Right? And what is that point, right? 2 over square root of 5, 4 over square root of 5. We might want to approximate rather than rationalize. So the coordinates will be approximately 0.894. I'll just write 0.89 is good enough. And then for y, we get 1.79. Actually, 1.8 would be good enough. Right, so 0.9, 0.8. Sorry, 0.9, 1.8. So where is that point on the circle? Well, I already highlighted it. I already circled it. It's about this point right here. So this point is our 0.9, 1.8. Right? You can see it's where the circle meets the level curve here, right? So, yep, so that's the point where we have presumably a maximum, right? So what is the maximum value then? So to get the maximum value, right, the maximum z value, that is, well, plug this number into the objective function, which was x plus 2y. So in this case, yeah, don't use the decimal. Let's get the exact value. Right. So we're going to use x is 2 over root 5 plus y, which is, I'm sorry, 2 times y. So 2 times 4 over root 5. We got 2 plus 8 is 10 divided by the square root of 5. But this we might want to rationalize, right? This is just going to be 2 square root of 5. So that should be the maximum value, 2 square root of 5, which is approximately what? 4.47, so about 4.5, so about 4.47. Okay, so take a look at the green line here. At least I was trying to make it green. The level curve of f that just touches the circle, that is tangent to the circle. This line right here. Remember earlier I said, look, it's somewhere between 4 and 5. So my guess was about 4.5, right? About halfway. And I wasn't far off, right? It's actually 4.47, which is very close to, 4.5. Yep. So at this point, right, where the green line, the green level curve of f is tangent to the circle, or where the gradient vectors are parallel, right? They don't have to be equal, but they do have to be either in the same or opposite direction. That should give you the maximum value, right? And we're done. Right? So that's how to find the maximum value using Lagrange multipliers. Right? And there's a bonus, right? Because remember, one thing I forgot about, or I hope you didn't forget about, remember lambda was positive or negative square root of 5 over 4. And we only looked at the positive. So what happens if we look at lambda is negative the square root of 5 over 4? Well, pretty much everything gets a negative sign, right? X is going to be negative 2 over square root of 5, right? And y is going to be negative 4 over the square root of 5. And when you plug those into the function to find z, right, you plug in these numbers. I forgot to do that up there. Negative. Yeah, you just get negative 2 square root of 5, or about negative 4.47. Right. So this, as a bonus, is the minimum value. They didn't ask for that, but there it is. So where is that? That's going to be at the polar opposite, right? So instead of this point on the upper right, it's this point down here in the lower left, right? And you can see that's where lambda is negative, right? Because the vectors, the gradient of f and the gradient of g, point in opposite directions. So, yep, at this point here, we expect lambda to be negative. At this point up here, we expect lambda to be positive, right? Right? Yep. And so you can see that's the green tangent line here. It's this line down here, right? Is somewhere between negative 4 and negative 5, and it's, well, negative 4.47. And so that would be the minimum value, which is, right, just the opposite side of the circle as the maximum value. Okay. And again, this is the two-dimensional picture. If it helps, right, let's revisit this picture here. If this is the xy plane, right, and then let's say, I'm using the wrong color here, but let's say this is the circle, right, x squared plus y squared equals 4, circle of radius 2. And now we draw the plane, right? Remember, the plane is coming out at you here, right? So this is a plane in space, but I'm drawing just the cross-section of the plane. That goes on forever. So this is z equals x plus 2y, right? So we can see at this point on the circle, and in fact we can label this point now, is 2 over square root of 5, 4 over square root of 5. That's the x and y. Right? That corresponds to this z value here. Z is going to be 2 square root of 5, right? And then for the negative value, right about here, so this has coordinates negative 2 over square root of 5 and negative 4 over square root of 5. And then this z value corresponds to negative 2 square root of 5. And that would be the minimum value, right? So you have the maximum value in red up here, and the minimum value in blue down here. All right? So this is the idea. This is how it works. Again, a very simple example that took a lot of explaining because we're still getting used to this Lagrange multiplier business. But right, so if you use the Lagrange multiplier equation here, right, you should get, in this case, 2 equations, but then you have to combine it with the constraint equation. Then you have enough equations to solve that system. Okay. Yeah, and we didn't have to solve the system this way. There's other ways of doing it, but in this case, I wanted to find the Lagrange multiplier first here, and then substitute that in the equations for x and y to get x and y. Okay, so there you go. There's our first example, and hopefully once you get used to this, we can solve some more complicated examples. But before we do that, maybe I'll show you the Calc 1 way of doing this, and hopefully you'll see you get the same answer here. All right, so just to remind you, here's the problem again. We want to maximize the function x plus 2y on the circle, right? So x squared plus y squared equals 4. That's our constraint. Right, so the way we did this in Calc 1, when we had no idea that we can take a function of 2 variables, well, you probably had an idea that you could, but we didn't know what to do with it, right? We're not at the level of Calc 3. In Calc 1, all we could deal with was finding derivatives of functions of one variable, like f of x, right? So we didn't have a choice here. In Calc 1, we had to take the constraint equation, and let's say we solve for y. So subtract x squared from both sides, and take the square root of both sides, right? And now we have the plus or minus, so that's kind of a nuisance. But we'll come back to the plus or minus later. So this is 4 minus x squared to the positive 1/2 power. So I can plug that into the objective function and reduce this to a function of just x. It's just x plus, well, plus or minus, right, 2 times the square root of 4 minus x squared to the 1/2. Now, obviously, I can't have a plus and a minus here, so let's take one at a time. Let's take the positive first, right? So this is now a function of one variable. You just take the ordinary derivative, right? We didn't know about partial derivatives in Calc 1. So the ordinary derivative is 1 plus 2 times 1/2 times 4 minus x squared to the negative 1/2 times the derivative of 4 minus x squared, negative 2x by the chain rule, right? So I think we just get 1 minus 2x over the square root of 4 minus x squared. And remember, in Calc 1, to find the critical numbers, we set this equal to 0, and we solve that equation. And we can solve that equation just by, subtracting the 1 from both sides and cross-multiplying. Oops, not 4x squared, 4 minus x squared, sorry. Right, so that equals 1. So 2x is equal to the square root of 4 minus x squared, square both sides, and then solve for x. So you're going to get 5x squared equals 4. So x squared is going to be 4 over 5. So x is going to be plus or minus 2 over square root of 5. Oops, make that clear. 2 over the square root of 5. And hey, look at that, 2 over square root of 5. That looks familiar, right? That's what we got way up here, right? Or better yet, down here, right? 2 over square root of 5. Same x, right? So yes, obviously we did not need Lagrange multipliers to solve this. We could have done it in the Calc 1 way, like we did here, right? Oh, and now that you know what x is, right, you can solve for y, right? Here's the function. And again, because of the plus or minus, you're going to get plus or minus 4 over square root of 5, which is the same answer you would have gotten using Lagrange multipliers, right? So yeah, so same answer using Calc 1. And admittedly, you probably are more used to this, more accustomed to doing it this way, and that's fine. But we'll quickly see problems later that we won't be able to do it that way, where we're going to have to use Lagrange multipliers. Or it's a lot easier to use Lagrange multipliers than to try to do it using this method here. Okay, so that's example 1. And we did it both ways. But let's get used to the Lagrange multipliers now. Okay, so here's Lagrange's theorem. We have f and g having continuous first partial derivatives. Another way to say that you have continuous first partial derivatives is to say that f and g are C1 functions. This means the C1 just means that the first partial derivatives are continuous. Right? So first partials are continuous. Right? If it's a C2 function, that means the second partial derivatives are continuous. and so on. But the book is not going to say that, so, right. So f and g have continuous first partial derivatives. And f has an extremum, so a maximum or minimum, at a point, x0, y0, on a smooth constraint curve, g of x, y is equal to c, right? And if the gradient of g is not 0, there's a real number lambda, such that the gradient of f is just lambda times the gradient of g, evaluated at that at that x0, y0, right? In other words, right, at the point where you have your maximum or minimum, the gradient of f and the gradient of g are parallel vectors, right? They point in the same or opposite directions. Right, so yeah, think of the picture we had at the beginning with the circle and then the level curves, right? And the gradients of that points in a certain direction, and the gradient of g for the circle, that points in a certain direction as well. So I'm not going to prove Lagrange's theorem. The proof is in the book. It's actually pretty short. It's maybe a paragraph or so and a few lines of calculation. So if you're into that kind of thing, if you're into proving things, then yeah, take a look. For our purposes, though, we want to use that theorem to essentially find maximum and minimum values, right? So for the method of Lagrange multipliers, right, so f and g, again, have continuous first partial derivatives, and we saw in the example that we did, those clearly have continuous partial derivatives. And f is going to have a minimum or maximum subject to the constraint, right? So to find the minimum or maximum, well, we write down the, I don't want to call it the Lagrange equation. I don't know what else to call it. What do you call this? Yeah, so this is just the equation involving Lagrange multipliers, right? So the Lagrange multiplier equation. Lagrange multiplier equation. Okay. Yeah, Lagrange's equation is very different, but we won't get into that, right? And the constraint equation, right? So this here is our constraint equation. When you put them together, you should have enough variables, right? So if you're only dealing with x and y, this is 3 equations and 3 variables here, right? So 3 equations in 3 variables. The variables are x, y, and lambda. Lambda is also a variable here, at least, right, if you don't know what it is initially. So then you evaluate f at each of the solutions that you get, right? We got 2 solutions in the last problem, right? And it turns out that one of them was bigger than the other. The biggest one, right, was the maximum, and the smallest one was the minimum, right? And that may not happen, right? Suppose you only get one solution here for this system of equations. If you only get one solution, then it's whichever the problem says. If the problem said to minimize a function, then it'll be the minimum. If the problem said to maximize the function, it'll be the maximum, right? It's not going to be a trick question where they tell you to maximize a function and it turns out to be a minimum, right? That would be a trick question, and we're not into that, right? The book is not going to do that. I'm not going to do that, so don't worry about that, right? If there's only one solution, it is the answer. It is the solution to the problem. It's either going to maximize it or minimize it, okay? Right. Yeah, but if there's 2 solutions, then you got to figure out which one's the maximum, which one's the minimum, right? And there could be more than 2. There could be 3 or 4. Again, just, right, the biggest one's the maximum, the smallest is the minimum. Okay, so that's the method. We did it already using in our first example, so let's try another example. Okay, so we want to minimize the function f as a function of x, y, and z, and the function is just x squared plus y squared plus z squared, subject to the constraint x plus y plus z equals 6, right? So here's our constraint function, or equation rather, x plus y plus z. And you can say minus 6 equals 0 if you want it to equal 0, but in general it equals some constant. In this case, 6 is fine, right? Yeah. So this is our constraint, right? And we want to minimize this function here. Okay. So this is going to be a little bit more complicated because it's a function of not just x and y, but a function of x, y, and z. Okay, that shouldn't be too bad. So, using Lagrange multipliers, let's write down the Lagrange multiplier equation. So we need the gradient of f. That shouldn't be too difficult, right? It's just 2x, 2y, and 2z. Right. We also need the gradient of g, and that's just going to be 1, 1, 1, right? So the partial of x with respect to x is 1, the partial of y with respect to y is 1, and so on, right? So now we don't set them equal to each other, right? We set the gradient of f equal to lambda times the gradient of g. So that means this is going to be 2x, 2y, 2z as a vector is equal to lambda times 1, 1, 1, which of course is just equal to lambda, 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 the three components. So when you set the x's equal to each other, the y's, and the z's, you get three equations. 2x equals lambda, 2y equals lambda, and 2z equals lambda. So we have three equations, but we have four variables, right? So what are the four variables here? We have x, y, z, and lambda, right? We don't know what lambda is yet. So we need a fourth equation. Where do we get our fourth equation? From the constraint, right? Remember, one of the equations here, using the method of Lagrange multipliers, has to be the constraint equation. If you ignore that, you're not going to have enough information to find either x, y, or z, or lambda, right? So yeah, you need the constraint equation as well. And in this case, the constraint equation is up here. It's just x plus y plus z equals 6. Okay. So again, there's various ways of solving this system of four equations and four variables. Let's do it the same way, the same approach that we did before. Namely, let's solve for x, right? X is just going to be lambda over 2. And likewise, y is going to be lambda over 2, and z is going to be lambda over 2. So now, plug each of these into the constraint equation, and you get lambda over 2 plus lambda over 2 plus lambda over 2 equals 6. So 3 lambda over 2 equals 6, which means 3 times lambda is equal to 12. And if you divide by 3, lambda is 4. Okay, but if lambda is 4, then x is going to be 4 over 2, which is 2. Likewise, y is going to be 2, and z is going to be 2. So there we go. We got one solution, 2, 2, 2, right, for x, y, and z. Okay, so did we minimize f? Well, first of all, I don't know. That's I guess we're being a little bit unclear here. What do we mean by minimizing f? So the minimum of f occurs at this point. The minimum of the function f occurs at the point 2, 2, 2. Okay. And the minimum value of f, right? We can't use z, so w is just going to be what, when you plug in x and y and z are equal to 2, you get 2 squared plus 2 squared plus 2 squared. So 4 plus 4 plus 4 is 12. Right. So 12 is the minimum value? Or is that the maximum value? Huh. Yeah, it does say minimize. It does say minimize, not maximize. Oh, maybe this is a trick question. Right? Because I guess I was expecting something negative for minimum, but look at the function f carefully. X squared plus y squared plus z squared. That has to be non-negative, right? Yeah, that has to be a non-negative function, right? The smallest value would be 0 at the origin, 0, 0, 0. But 0, 0, 0, 0 plus 0 plus 0 does not equal 6. It's not on the plane. It's not part of the constraint, right? So no, I think this is the minimum value. The minimum value is 12, right? And it occurs at the point 222. So this should answer the question, right? So the minimum value of f is 12 at the point 222. Okay. Yeah, now again, how do we know that that really is the minimum and say not the maximum? So it turns out I don't think there is a maximum here, right? There is no maximum. It's only a minimum. Okay, so think about what we're doing here. I think we did something like this in the last section. What is this function f here, right? This function f, let me just copy it down again here. X squared plus y squared plus z squared. Right? This is the function that I called s in the last video, right? This is the square of the distance from the origin. Square of the distance, right, from the origin 0, 0, 0. Right? Right? If you take the square root, you get the distance from the origin, right? So we're trying to minimize the distance, or the square of the distance, either way, from the origin to the plane, right? X plus y plus z equals 6. So yeah, if we graph the plane, let's do it this way. So this will be the y-axis, this will be the x-axis, and this will be the z-axis here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Perfect. So the plane, I guess I'll draw that in yellow, is going to look like this. Let me try that one again. Yep. Again, that's just a portion of the plane. This extends infinitely in all directions, right? And keep in mind that the origin is right here, right, which is through the plane, right? It's inside of it, right? Or maybe if that picture doesn't help, let's do it this way, right? Here's the xy plane, here's the z-axis, and then the plane, oops. Yep. So this is the plane x plus y plus z equals 6. Or if you like, z is equal to 6 minus x minus y. Same thing. Right? Right. And so here's the origin. So what point on the plane has the shortest distance to the origin? It's probably not this point up here. It's probably not this point way over here, right? Because this point's a little closer. This is closer. Right about here, I think we get the minimum distance, right? So that distance should be 12. Sorry, square root of 12. Right? Remember, SF is the square of the distance. If you want the distance itself, don't forget to take the square root, right? And then this point on the plane right here is the point x equals 2, y equals 2, z equals 2. So z is going to be 2 here, and then x and y, this point right here below it will be the point 2, 2. So yeah, very difficult to do this over here, but right around here, I guess, is the point. If we go down to the surface, we get x equals 2, y equals 2, and z equals 2. And then this distance would be the square root of 12. So bad orientation to kind of see it there, but the picture on the left might make a little more sense. Okay, so yeah, we did something like this in the last video where we minimized the distance to the origin, or the square of the distance to the origin, to some surface. The surface in this case is just a plane. I forgot what the surface was in the last video. It might have been some sort of a paraboloid or something. But it's the same idea, right? Okay, so yes, obviously we did not have to use Lagrange multipliers. What we could have done is solve for z, right? And then just plug that expression into this, and then treat that as a function of two variables, and then find the critical points, and so on, right? So that's what we did in the last video, right? And maybe you like that way better. Okay, that's fine, but you might want to get used to Lagrange multipliers. For one thing, you know, in one question it might insist that you use Lagrange multipliers to solve it. So I could ask for either way, either by substitution or by Lagrange multipliers. And so here's one of those problems. This, again, I think I took right out of the book. Use Lagrange multipliers, right, to find the highest point on the curve of intersection of the two surfaces. The first surface being the sphere, right, x squared plus y squared plus z squared equals 36. You know, and they tell us it's a sphere, although I hope you know that by now, right? It's the sphere centered at the origin with radius 6. And the plane, 2x plus y minus z equals 2. And again, you know that that's a plane, but they're just helping you out a little bit there, right? And so, yeah, so the question is, what is the highest point on the curve of intersection? And while this is going to be very difficult to draw here, here's the sphere. Suppose the radius is 6, right? Here's the center. So that's the sphere. And then the plane, well, something like this, right? Suppose the plane slices the sphere, and you get something like this, right? So that looks like a circle to me. In fact, that should make sense, and I think we've seen that before, where if you take a plane and slice it with you take a sphere and slice it with a plane, you get a circle, right? And so what they're asking for is, what is the highest point on that circle? It's right about here, right? And right around here would be the lowest point, but that's not the question. Okay, so we want the highest point, right, on that circle. Okay. So, and specifically we have to use Lagrange multipliers, right? So here's the tricky thing, right? These equations here, the sphere and the plane, these are not the objective functions. These are both constraints. So we have two constraints, right? Right? Because this point here, the highest point, has to be on the sphere, and it has to be on the plane. It has to be on both of these surfaces, right? After all, the circle is the curve of intersection. It's on the plane, and it's on the sphere. It's on both, right? And so that's true for the highest point as well, which is on the circle of intersection, right? Okay, so these are both constraints, right? So yeah, let's call that g of x, y, and z. It's just x squared plus y squared plus z squared equals 36. And I guess we'll call the other one h. It's just the next letter down the alphabet. So 2x plus y minus z equals 2. So, but that raises the question then, what is our objective function? What are we trying to do here? Well, we're trying to find the highest point, right? What do we mean by the highest point? Well, we have the z-axis, right? The x-axis and the y-axis. We're looking for the point with the highest z value. So our objective function, which I'll call f, we're trying to maximize z, right? Just z. Right? The highest point is the point where the z value is largest, highest, right? So yeah, they don't make that clear in the problem, but when they say the highest point, they mean, right, z is going to be largest there, right? At every other point on the circle, z will be less, z will be smaller. So we want the highest point on that circle, on that red circle there, right? All right, so we have all the information now, right? We have f, and we have the two constraint equations, g and h. So this is getting a little complicated now because this Lagrange multiplier equation is not enough because we also have h. So it turns out we're going to need two Lagrange multipliers, right? One for the gradient of g and then another for the gradient of h. So the Greek letter we'll use will be mu. So this turns out to be the Lagrange multiplier equation for two constraints. Right. And of course you can have 3 constraints or 4 constraints or 5 constraints, but I think in the homework problems as well as on the practice and the tests and all that, at most 2 constraints. In fact, usually just 1 constraint. But I wanted to do one where there might be 2 constraints, and this is such a problem, right? Okay, not an easy one. Not an easy one as we'll see here. So first let's take the gradient of f. The gradient of f, well, oops, sorry, f. So the partial of f with respect to x is 0, the partial of f with respect to y is 0, and the partial of f with respect to z is 1. Right? So we just get 0, 0, 1. Right? And now the gradient of g, well, we did that before, right? We did that in the previous problem. It's just 2x, 2y, and 2z. And now the gradient of h. So that's going to be 2, 1, negative 1. Right? So when you set the 3 components equal to each other, you get a system of 3 equations. I'll put the 0 on the right here. So we're going to get 2 lambda x plus 2 times mu is equal to 0. We're going to get 2 lambda y plus 1 times mu is equal to 0. And then we're going to get, let's see, 2 times lambda times z minus 1 times mu, so minus mu, is equal to 1. And there's 3 equations, right? Unfortunately, we have 5 variables now. Obviously, we're looking for x, y, and z. But we don't know what lambda is, and we don't know what mu is, because we have 2 constraints. We have 2 Lagrange multipliers. So these are, right, both Lagrange multipliers. So, yep, we have 5 variables, x, y, z, lambda, and mu, but we only have 3 equations. Of course, the other equations will be the constraint equations up here. So let's write down the constraint equations, or let's copy, I guess I'll just copy them down for reference. So there's G, and here's H. Okay. So we have 5 equations and 5 variables, and it's a nonlinear system. All right, so this could be a bit of algebra here. All right, so let's see what we can do here. So my strategy, as before, is to see if we can find values for lambda and mu first. Right. We don't have to take that route, but let's see if we can do that here. So I'm going to look at this third equation here. Right? We have 2 times lambda times z minus mu is equal to 1. But we know what z is in terms of x and y. So take the fifth equation here, and let's solve that for z. Right? Z is going to be 2x plus y minus 2. So I can take this expression and plug it in here. And if I do that, what do I get? I get 2 lambda times 2x plus y minus 2 minus mu equals 1. And if we untangle that, we get 4 lambda x plus 2 lambda y minus 4 lambda minus mu equals 1. Okay, so I guess that's an equation. What can we do? We can factor out a lambda here. I don't know if that's going to help. And we're going to get 4x plus 2y minus 4, and then minus lambda equals 1. Okay. Well, that's one equation in 4 variables, x, y, lambda, and mu. And then we have these equations here. Let's see if this works. Oh, I know what mu is. Mu in the second equation. So I should label these, right? Equation 1, equation 2, equation 3, equation 4, and equation 5. So this was equation 3, and this was obviously equation 5. So let's look at equation 2. Equation 2 says mu is equal to negative 2 lambda y. So that means I can replace mu with negative 2 lambda y. It is minus mu, right? Yeah. The minus came from yeah, the gradient, right? So the gradient of f is 1. Oh, I'm sorry, the gradient of h. Yeah, negative mu. Okay, just checking. All right, sorry about that. All right, so this equation then becomes 4 lambda x plus 2 lambda y minus 4 lambda plus 2 lambda y equals 1. We can combine these and get 4 lambda y minus 4 lambda equals 1. We can factor out a 4 lambda here and just get x plus y minus 1 equals 1. Hey, it's progress, right? We're down to, we had 4 variables, now we only have 3. Okay, now what? Well, I think we haven't used the first equation yet. The first equation just says that 2 lambda x plus 2 times mu equals 0. But look, now we know what mu is. Mu is negative 2 lambda y. So that tells me 2 times lambda x minus 4 times lambda y is equal to 0. And if we factor out a 2 lambda, we just get x minus 2y is equal to 0. So this actually tells me a great deal. It tells me that either lambda is 0 or x is equal to 2y. Okay, and we'll just have to take each of these separately. First, let's look at x equals 2y. Right? If x is equal to 2y, and I plug that in here, I get 4 lambda times, well, 2y plus y minus 1 equals 1, which is 4 lambda times 3y minus 1 is equal to 1. And that's a little bit better. But it doesn't equal 0, so be careful. Y is not 1/3 here. But look, we can also figure out what z is. By the fifth equation, just to keep this straight, we have z was 2x plus y minus, 2x plus y minus 2. But if x is equal to 2y, we have that z is equal to 4y plus y, so that's 5y minus 2. Okay. So that's looking a little bit better. And I think the only equation we haven't used yet is 4. So let's get to equation 4. X squared plus y squared plus z squared equals 36. And x is 2 times y. I'll leave y as y squared, right? And then z is 5y minus 2 squared. There we go. I think we can solve for y. Not easily, of course, but let's try 4y squared plus y squared. And then multiplying this out, we get 25y squared minus 10y plus 10y, 20y, plus 4 equals 36. So 5y squared plus 25y squared is 30y squared minus 20y, and then 4 minus 36 is negative 32. So we get a quadratic equation, and we can just use the quadratic formula. Maybe before we do that, why don't we just divide by 2 to make it a little bit easier. Right. And yeah, I don't feel like trying to factor today. Let's just use the quadratic formula. So negative b is 10 plus or minus the square root of b squared minus 4 times a times c. So these will definitely be real numbers. I was worried we would get, imaginary numbers and then the whole thing would fall apart. So what are we going to get? 10 plus or minus the square root of, I'm sorry, not 100 squared. That's just 10 squared. So I already squared the 10. That's 100. 100 plus 4 times 15 times 16. So I get 1060. Oops. All over 30. 4 times a times c. Yeah, 10 squared. I think that's it. Right? So 4 times 15 is 60 times 16 is 960 plus 100 is 1060. And then, oops. Yeah. So the square root of that is whatever it is. I don't think there's a way to simplify that as far as I know. Well, okay, 2, yeah. So it's 10 plus or minus 2 times the square root of 265 over 30. So I guess we can factor out a 2. So 5 plus or minus square root of 265 over 30. over 15. Yeah, divide by 2, right? So divide top and bottom by 2. So 30 divided by 2 is 15. Phew, almost missed that. Yeah, not very nice numbers here, but okay. Well, look, we're almost done. Now that we know y, we know x, right? Remember, x was just 2 times y. So x is going to be 2 times y. So yeah, 10 plus or minus 2 squared of 265 all over 15. So that's for x. And then z, of course, will be 5 times y minus 2. Do I even dare do that? So 25 plus or minus 5 squared of 265 over 15 minus 30 over 15. And so that's going to be negative 5 plus or minus 5 squared of 265 all over 15, which is negative 1 plus or minus the square root of 265 all over 3. Great. So that's x, y, and z. Who cares about lambda and mu, right? These three will be the points on the circle up here with the biggest z value. So I don't think we want the negative here. I think we want the positive answers, right? So the highest point, because the negative would give you probably the lowest point. So the highest point on the curve of intersection is, so x is going to be, oh, where's x? Yeah, 10 plus or minus 2 square root of 265 all over 15. So not plus or minus, right? Just plus for the highest point. And then y is going to be 5 plus square root of 265 all over 15. And then z will be negative 1 plus the square root of 265 all over 3. And those are the exact coordinates. I know for you engineers out there, you want the decimals. Okay, here they are, right? So just plug them in your calculator. 2.837 for x, 1.419 for y, and 5.093 for z. And so, yeah, the highest z value, right, the highest z value here is, again, approximately 5.1, or more precisely 5.093. So that's as high as it gets on the circle here. Right? And if you want the lowest points, just take the negative signs instead of the positive signs for x, y, and z. And that'll give you the lowest point. Right? So, and I'm pretty sure it would be negative. Just to get the z value. I'm getting the lowest z value. Right? Is negative 5.759. Actually, negative 5.760 to 3 decimal places. But again, they didn't ask for that. They asked for the highest point. And we did it. Not pretty, right? I know a lot of work here, so let me just quickly go back. Right? We're looking for the highest point, so our objective function is f of x, y, z equals z. We only care about the biggest z value. But we have two constraint equations, the sphere and the plane. So we needed two Lagrange multipliers, lambda and mu. Right? And that created a system of 5 equations and 5 variables. And look, at the end of the day, you know, you can easily just take this system of equations and, you know, plug it into your calculator or a computer. Oh, it's nonlinear, so that might be tricky. But yeah, if you use a computer, Wolfram alpha will spit out the answer pretty quickly. But just to be aware that it is doable just using basic algebra here. It's not easy, right? It's a lot of back and forth, and probably, you know, I might have done this the quickest way possible. There's easily like wrong terms you can make here, if you especially if you miss a minus sign or something, you know, something careless like that. I'm almost surprised that I didn't make such a mistake. I almost did, but not quite. All right, so that's Lagrange multipliers, right? This would have been a very difficult problem to do without Lagrange multipliers, and I would, you know, maybe encourage you to try to do that, but that's, you know, that would be much more difficult, I think. So yeah, that's the idea of Lagrange multipliers.